So this is the fourth and the last installment in this lecture series on quantum biology, and today I'll be speaking about aspects of quantum biology related to neuroscience. Last time we talked about microtubules being potentially intracellular objects which interact with electromagnetic radiation, perhaps even trap quantum states. And today we'll see the consequences of this hypothesis in the context of things like memory, anesthesia, neurodegenerative diseases, etc., of great importance to our understanding of how the brain works. So we are looking at this nanoscale molecular biosystem, which is the microtubule that actually performs numerous functions in various cells, all eukaryotic cells, and especially important functions in dividing cells and in neurons. This structure enters into more complex arrangements, making bundles of microtubules in neurons, making mitotic spindles in dividing cells, as well as providing the structural input into the building of centrioles and centrosomes. And we've seen last time how important they are in terms of cellular intelligence, as postulated by Albrecht Piller, etc. So, in addition to this, they interact with other structures in the cell, as you will also see, including ion channels, actin filaments, and the membrane. What's interesting, and I don't have the time to go deeply into this topic, but you can look up the review paper which is listed on this slide. The microtubules have quite amazing electrical properties, which is of relevance here because that may enhance the ability of microtubules to interact with electromagnetic radiation, being themselves highly charged, and it has been demonstrated by various experiments that they affect the ionic conductivity in solution, such as in cytoplasmic solutions, and the question is, what is conducting ions? Almost certainly, perhaps also protons, because we know that there is an effect on mobility as a function of pH. It's potentially also electrons, but that has yet to be demonstrated. Although we have indications that electronic conduction also plays a role, which would be closing the loop in terms of our understanding of this entire group of mechanisms, including electromagnetic excitation of quantum states in microtubules. We know that microtubules interact with various external probes at different frequencies, so they have a range of frequency-dependent resonant or quasi-resonant responses. They are very sensitive to high-frequency ultrasound, so there is an acoustic interaction with frequencies to about 500 kilohertz to 1 megahertz. They respond very strongly to electromagnetic fields via ionic conduction effects in the range from 100 kilohertz roughly to 1 megahertz. They also have a strong dependence on electromagnetic radiation in the terahertz, low terahertz region by actually undergoing conformational transformations to the point of breakup. And we believe that they have electronic responses to electromagnetic radiation in about 500 terahertz range, and excitonic predicted by computational modeling in about 600 terahertz. How that changes on constructing architectures for microtubules inside the cell or artificially, we don't quite know yet, but it could be quite sensitive to the arrangements, whether it's parallel bundles or interconnected microtubules via MAPs, microtubule-associated proteins, or radial arrangement in asters in cells. All of this can depend on the geometry and may be specific to it. So that opens a huge area of our investigations on the experimental front of how intracellular structures sense and respond to electromagnetic fields in various ranges. So having said that, now the question arises, what does it have to do with the issue of the human brain, its processing, its architecture, and its capabilities? Well, I'll address some of this. This is an enormous area that requires much greater time development and dedication to it. But there are some very fundamental questions which we believe quantum mechanics can, if not answer, then at least help us understand better. And these questions, in the maybe order of significance, are: what is consciousness? It's an age-old question that has been addressed by very many brilliant philosophers, physicists, cognitive scientists, and neuroscientists, and we still don't have a very precise answer to the question, or even approximate, I would say. But maybe we're getting closer by bringing quantum mechanics to this question. Roger Penrose wrote two major books in this area, The Emperor's New Mind and the second book. Anyway, you can look up Roger Penrose's books, where he gave very strong arguments in favor of non-algorithmic and certainly not classical operations of the brain. And the question is where this might be happening inside the brain. And so the second question, maybe a more precise question to address, is where is memory stored? Or is it stored? Or is it even inside the brain or somewhere else, accessed by the brain? Maybe not only in the brain. The next question, which is quite precise, will actually address it quite clearly, is what is the computational power of the brain, maximum power of the brain, understood as a computational device, organic matter that performs definitely some sort of operational function, information processing, storage, retrieval, etc. The question then is information processing in the brain classical, quantum, or maybe some combination, hybrid, or perhaps even fractal? That is, there are layers in a hierarchical organization of the brain that store, process, and retrieve information, perhaps in an interactive feed back and feed forward manner. And then the last one, which being a physicist really caught my attention, is in terms of the energetics of the human brain, which is orders of magnitude more efficient than comparable man-made structures, computers, computing devices, electronics, etc. But I will start with a very controversial, in my opinion, statement by Robert Epstein, posted about 4 years ago, less than that, an article called "Your Brain is Not a Computer," stating, I would say yes, it's not a computer as we know it, but it's a computational structure, organic living structure, not a computer. It's not plugged into the electrical outlet. It's powered by quantum biological energy, ATP. And then further down in the article, Epstein says, your brain does not process information, retrieve knowledge, or store memories. In short, your brain is not a computer. I think this is complete nonsense. It's not even a serious proposition, because we know that the brain stores memories. We can retrieve them, and we can also, of course, we lose some of it. Some attrition occurs. It processes information every time we look at the environment, we respond to it. That's information processing. If we solve a mathematical equation, we process information. If we play a game of chess, we constantly process information, inputs and outputs in terms of the moves we make on the chessboard. So I don't think how anybody can say that. And then I think the next paragraph illustrates the fallacy of this kind of thinking. Namely, it says, no matter how hard they try, brain scientists and cognitive psychologists will never find a copy of Beethoven's Fifth Symphony in the brain, or copies of words, pictures, grammatical rules, etc., etc. So, obviously, you cannot find a book in your brain, you cannot find a symphony or pictures, but we have representations in different form. We don't know exactly how they are represented. We don't know the memory code, and I will actually address it. We perhaps have some inklings of what it might be. Just like you cannot find a copy of Beethoven's Fifth Symphony in a memory stick or a computer memory, but it's encoded in terms of a binary code, zeros and ones, and then can be transcribed into notes, and music can be produced by mechanisms that interface between electronic and acoustic degrees of freedom. So that seems to be a fairly misguided approach to it. Things are much more complex than just storing books in your brain. So let's take a look at the brain from sort of a physicist, mathematician's perspective. And I will address the questions of power and information processing, information storage, and the cost of it, because there is a cost to storing and retrieving information. And that's why the brain actually is the most energy consuming organ in our human body. It takes about 25% of all the power generated from nutrition, being only about 1/50th of the weight, 2% or so. So it's 10 times more demanding, it's more demanding energetically than the average for the body. But that still actually is quite tiny compared to, as I mentioned, man-made devices that process information or store information. So the brain is composed, roughly speaking, of about 100 billion neurons and glia, probably more glia than neurons. We typically focus on neurons, but glia and astrocytes and other types of cells in the brain perform equally important function. Today I'll just focus on neurons because we believe that these are the structural elements that store and process information. So 100 billion, 10 to the 11th of these cells, and what's important is that they communicate constantly with their neighbors, and on average each neuron interacts with about 10,000 other neurons, exchanging signals, and in some cases up to 100,000. So you can think about the society of neurons forming one brain as comparable to an overpopulated planet with 100 billion people, let's say. We have roughly 8 billion people today, 7.8 or something on this order. So that would be 10 times greater population if you take one neuron as representative of one member of our human society. And they interact with 10,000 other neurons, so you have to project it on us. Can I say that I interact with 10,000 on a regular basis, other people? With proper, of course, current technology, we can, as some people do, on Instagram and Facebook and through Twitter, and some people even interact with more. So we can start approximating the complexity of the brain by the complexity of the human interactions currently. Okay, so that makes about 10 to the 15th synapses, because a synapse is a structure inside dendrites that interacts with neighboring neurons. And now the question arises how frequently these signaling events occur, and estimates vary, but even if it's only, I would say typically it would be probably on the order of milliseconds or a millisecond, but even if we say 10 impulses per second, then we have 10 to the 16th synapse operations per second in the entire brain, which is an enormous number. That actually can be compared to one of the most powerful computing clusters built to date, the Blue Gene computer made by IBM, which operates at about 10 to the 15th operations per second. So that's about 10 times more if we extrapolate to the brain. So 10 times more operations per second than the Blue Gene, which has something like 100,000 processors or more. Yet, the power consumption of our brain is minuscule by comparison. About 25 watts, which is 25 joules per second, compared to 1.5 megawatts for the IBM's Blue Gene, which is more or less the consumption of a town comprised of about 30,000 people or so. So the comparison is about 6 orders of magnitude, a million times more energy intensive is the computer cluster than the human brain. Actually, it's even probably more, because 25 watts is what the brain uses for all of its operations, which includes temperature, constant temperature of 37 degrees Celsius or so, as well as protein synthesis, maintenance, transport, trafficking of molecules, etc. Therefore, you can estimate probably the computational or cognitive cost to be about a tenth of this. So I would say 3 to 5 watts, which is really, really tiny, and that should be compared to 1.5 megawatts. All right, so that's the first enigma. How does it happen? How is it so efficient? One possible answer, of course, would be to assume there's some sort of quantum computing taking place, which is incredibly efficient in terms of exploring the space of solutions for any problem to be solved. So the question is quantum mechanics relevant to the brain? I believe so. It may be a quantum computer. Again, the word computer is somewhat tainted with our biases as we use computers for various purposes. The brain is, in my opinion, a supercomputer cluster of some kind, or supercomputing cluster. In fact, evolvable, as we know, because learning, development of the brain in early childhood and early adulthood takes place and continues maybe up until the age of 20 or so. It's always evolvable, and past that, our learning and experiences change the synaptic connections. If you acquire a new language, you'll acquire activity of the brain in various areas that before were not activated. So that's a very dynamic situation. Some people, such as Stuart Hameroff and Roger Penrose, propose that our thoughts are examples of wave functions because they are non-localized. That is, we don't know exactly what the thought is, this neuron, that neuron. Actually, I would say probably in the entire brain. And it could also be a superposition of different thoughts at the same time if you're trying to decide whether to, in the trivial case, order a pizza or sushi for dinner. And before you decide, you're in a state of superposition of two ideas in your head. And then when you do decide, or when you decide to go to the movie or stay at home, you make a decision which is almost like a wave function collapse. That is the measurement. That is the outcome of your processing in the brain. So there is a lot of, at least metaphorical, comparison that can be made between how we think and how quantum systems operate. This brings also the issue of the existence of quantum mechanical limits. We have talked about this, that in classical physics we don't have these limitations on the precision of measurements, simultaneous measurements of position and momentum, energy, time. Whether if this can be translated into the human brain, perhaps we also have inherent limitations on the perception of reality, because this would be quantum mechanically embedded. And that also finally has incredibly interesting implications for artificial intelligence, which currently we're, as a society, are enamored with. Artificial intelligence, machine learning seems to be perceived as a panacea for all the otherwise impossible questions to resolve, and we rely on computers to solve these problems for us without understanding the meaning of these solutions. Perhaps, to my knowledge, all of artificial intelligence is actually classical thinking, classical algorithms, although perhaps in the future there will be quantum. But if they are not quantum, then my conclusion would be that artificial intelligence will never be able to approximate the power of human intuition, thinking, which is sometimes based on glimpses of observations, patterns that we recognize with very fragmentary knowledge. I'm sure most of you listening and watching this video experience this when you see somebody in the corner of your eye crossing the street, just by some features, maybe the gait or the type of movement, you can recognize this is your friend or this is your family member, and an algorithm might not be able to do it because it's the information input into this process is so small. Okay, so having set the stage, now we'll look at what may be happening at the molecular scale. We have to go down in scale of physical sizes and times, as well as energies, in order to understand if quantum mechanics can be implicated in these processes. And the functional unit, as I mentioned to you earlier, is the neuron, nerve cell. And I mentioned the theory of orchestrated objective reduction proposed by Hameroff and Penrose some almost 25 years ago, I think in 1996, which is to date still very controversial, still not widely accepted, but the only molecular level theory of consciousness. And it actually states that quantum processing is involved in consciousness, and this quantum processing actually has a very specific substrate where these wave functions are present and collapse, as I mentioned in the thought process, and that is at the level of microtubules, and more specifically the building block of microtubules is a protein called tubulin. The stable form of tubulin is an alpha-beta heterodimer, and this structure is about 8 nanometers by 5 nanometers by 4.5 nanometers in dimensions. Its mass is equal to about 110,000 proton masses. So that's a very large mass to support a quantum state. But I mentioned to you earlier, I think in the second class, that we now have evidence coming from experimental physics that quantum states are supported by objects, proteins, about a quarter of that size. So it's not a big stretch to imagine that the wave function of a tubulin dimer may exist. And furthermore, it may actually be entangled with other tubulins in a microtubule, and a microtubule consists of consists of 13 protofilaments, and the length varies, but let's say maybe 10 nanometers long, which would be 1,250 rows of 13 tubulin dimers each. So let's say 16,000 or so tubulin dimers in a microtubule could be in an entangled state, and the transitions between different states are envisaged by Hameroff and Penrose as qubits. We talked about qubits in the context of quantum computing. There could be two states or more and that tubulin can adopt and switch between. And this switching of states, therefore, would correspond to some form of information, quantum information processing. In a cell like neuron, you can have a few thousand microtubules, or on this order, and all of these microtubules can support individual quantum states, or maybe can be entangled in a collective state. So let's take a look at the organization of microtubules inside neurons, especially dendrites. Here you see a micrograph of bundles of microtubules interconnected by microtubule-associated proteins, right here, which make them structurally stable and form a network somewhat similar to parallel networks in logical devices. And that's on the left is a cartoon of a dendritic tree with a synapse and actin filaments going into the synaptic batons, and maps interconnecting microtubules, as well as well, that's about it. The only thing I want to say is that the separation between microtubules is somewhere in the range of 90 to 100 nanometers. So they are not very close, but close enough. And there are various issues regarding structural stability of microtubules in neurons that lead to pathologies. I'll mention that briefly later on. Because these pathologies reflect not only functional disorganization or of the cytoskeleton, but also the consequences in terms of the dysfunction, loss of function, loss of ability to provide cognitive functions. All right, going down, we have a single bundle of microtubules. This is a single microtubule, and its building blocks, tubulin alpha beta dimers. It is believed in neuroscience that our cognition mainly takes place in dendrites. Dendrites are connected to other neurons, so this is where the information exchange of signaling takes place through synaptic connections. And I want to mention one aspect of dendrites which is quite specific, namely that the microtubules, which are cylindrical in shape, they also have a direction, that there is a plus end of a microtubule and a minus end of a microtubule. Plus end is typically related to faster growth and minus to shrinkage. But we know also from the directionality of motor proteins, in particular kinase and dynein, these moving proteins that carry cargo, such as neurotransmitter material, they move in specific directions, kinase into the plus end, dynein to the minus end always. So you have almost coordinated traffic like on divided freeways. Why is this important? Because in dendrites, and only in dendrites, as far as we know, microtubules are organized in an antiparallel fashion. So the neighboring microtubules always have the opposite direction to the one that you are focusing on, and it's alternating. So that you could see it as some sort of network of parallel highways with separated directions, lanes going to the plus end, lanes going to the minus end, etc. This could be a way of backpropagation of signals or communication, or maybe recycling of the vehicles, motor proteins that are circulating the material. Microtubules also are known to directly interact with ion channels, especially voltage-dependent anion channels. They regulate them. So it's not just a static device, but a static roadway for motor protein transport. We know it's dynamic because it's also used in cell division, provides the force for chromosome segregation. But we believe it's much more than that. But here we see that it's microtubules, especially there's C-termini, which are flexible, negatively charged protrusions from the surface, can open and close ion channels on the cytoplasmic side. So they interact with receptors, therefore can be used for the communication purposes with the outside world to the cell and signal processing into the cell. There was a very, in my opinion, important, perhaps overlooked paper in Science about 1997 or so, now more than 2 decades ago, which reported, this was the work of Donald Ingber and Andy Maniotis from Harvard, who demonstrated that microtubules send mechanical signals from the cytoplasm into the nucleus. So there's also mechanical communication in addition to electronic or electrical signaling. All right, so this is the structure of microtubules just very briefly. There's a huge literature on it from crystallography, from electron crystallography earlier on, from X-ray crystallography more recently. We have the crystallographic structure of the building block tubulin. We know microtubule organization. There is a hollow interior, which we still don't know what's going on there. It could be a safe channel of communication, if you will, a protected channel of signaling inside the cell, which is undisturbed by the goings-on inside the cell. It's about 15 nanometer diameter lumen that could be serving these purposes. So it shows how microtubules are built from strings of tubulin dimers, which we call them protofilaments, and there are 2 types of lattices. So they are very regular, probably the most regular structures in all of biology, maybe except for the tobacco mosaic virus. Hexagonal structure and regular surface, highly periodic, but 2 lattices exist, the so-called A lattice, which is completely perfectly periodic, and that type of lattice of microtubules is almost exclusively found in neurons, perhaps for a reason. The more common, maybe 99% or so of microtubules have a B lattice, which has a seam, i.e. there is a discontinuity line along the axis. When you wrap up the sheet of tubulin, it will not be perfectly folded, but it will be somewhat shifted by so-called offset. There is some interesting potential for electronic degrees of freedom. We have found some time ago some computer simulations that there is between the alpha and beta tubulin dimer, there is a double well structure from the electronic point of view, and electrons could hop between the 2. This might be the 2 wells. This might be a natural place to look for a concrete realization of a quantum state. This was actually predicted a long time ago, now more than 3 decades ago, by Stuart Hameroff in his visionary book called Ultimate Computing, dating back to 1987, if you believe it, where he predicted microtubules to be computational devices in our brains. So, without going into detail, I'll just tell you what, in my opinion, is the amazing potential for computing using tubulin dimers, either in nature or in artificial structures which we can build by forming microtubules in the lab. So number 1, the C-termini, which I mentioned to you, these electrically charged protrusions, they can be in at least 2 states per monomer. They can be stretched out or folded onto the surface, which gives you 4 possible states per dimer. The electrons I showed you, 3 electrons can hop. Maybe these are the same electrons which we can activate by the 630 nanometer light that Dr. Legario showed in his experiments. So electron hopping could occur maybe also 4 states per dimer, 1 state per monomer, 2 states per monomer. This is well known. Each tubulin dimer can exist in 2 conformational states, which means structurally shifting. There's basically a hinge motion between alpha and beta dimer that is energy dependent. And when GTP hydrolyzes on the beta tubulin, it causes a conformational shift by about a 30-degree to the axis movement or rotation of the beta monomer. So here we can have 2 more states. And there could be additional states related, one of which I will mention later. For example, phosphorylation states. Phosphorylation is one of the key signaling phenomena in cell biology. Phosphorylation activates molecules such as enzymes, and dephosphorylation deactivates. So maybe some other ones, such as phosphorylated states in tubulin or excited states in tryptophans, I will also mention later on. But if we stay with the first 3 possibilities only of building states inside microtubules, that is C-termini states, up-down, electron hopping states, and conformational changes. So we know the C-termini states, by the way, that is quite well. We end up with about 32 states per dimer, and if you calculate the number of states, the size of a microtubule, that I mentioned to you, about 16,000 dimers, then you build up a huge amount of state space. In fact, 100 kilobytes in terms of information content could be packed into a microtubule, and if you multiply by the number of microtubules on the order of a few thousand per neuron, that will give you the number of 1 gigabyte storage per neuron. That's an important number to remember. It used to be the size of a memory stick, 1 gigabyte. Now we have much more powerful memory sticks, but 1 gigabyte is not too bad per neuron, since we have, as you remember, 100 billion neurons, which means that if all neurons are equal, and they are not, but for the sake of calculation, you would end up with 10 to the 20th bits per brain, which is an enormous amount of information storage capability, which we'll come to in a second. What does it mean practically? But I would hypothesize that this is enough to store all your lifetime's memories in your brain if you were able to encode or use a read function in microtubules. And read in and write and read, I should say. Now the second question is, all right, storage, lots of memory. Can you write and read? How fast can you do it? And that is a very important question, because I told you about half an hour ago that there's a very finite amount of energy or power supply given to the brain, about, for these purposes, about 5 watts. So the question is, how much processing, information processing, can one do with this limited power supply? And this depends on the rate of transitions, state transitions. If these transitions are on the microscopic scale, you could expect picosecond or nanosecond. Now nanosecond will be already slow transitions. But if these microtubules could switch states on a nanosecond scale, then we would end up with about 10 to the 27th operations per second in the brain. This number is astounding. Remember, we talked about the blue gene, 10 to the 15th. That would mean a trillion blue gene computers in your brain. But I'd say that's not possible, and I'll explain to you why. Simply because of the energy limitations. If we could do so many processing operations per second, the brain would basically explode as a result of the heat release. Because each operation, there's a theorem in information science called the Landauer theorem or equation, which equates one bit of information with the energy of kT logarithm 2. In other words, this is the amount of energy, minimum amount of energy you need to introduce to erase one bit of information and replace it with another. So, but in biology, actually, biology is by definition, and we talked about this, limited from below by thermal energy, which is free. So we cannot assume that thermal energy is enough to erase information. That would make biology unsustainable, because all thermal noise would constantly erase all biological information. For this reason, I would say the biological Landauer equivalent would be ATP energy, because you need ATP or GTP for any deliberate biological step or biochemical reaction. Therefore, you have to at least provide that much to encode or decode information. So, with this, you can easily calculate how many bits of information per second one can have. That, by the way, is in this slide. It's maybe a lot of information on a very small slide, but I'll point out to the key elements of it. So the energetic requirement for a bit of energy in biology, in my opinion, would be something like 5 times 10 to the minus 20th joule, which is ATP energy. You have to have at least that much energy to encode one bit of information in a biological system to be stable, because if it was much less, it will be erased by thermal noise. You don't want that. So with the 5 watts or so of energy supplied to the brain constantly on average, you end up with a very simple number to remember, that is our maximum information processing capability at the brain level. In my opinion, it's 10 to the 20th bits per second. Easy to remember, 10 to the 20th. I don't think we can exceed that number, and probably we never even approximate it. But perhaps people like Einstein, at some points in their brilliant lives, were able to approximate this number with the intellectual power. At any rate, now the question arises, what does it mean per neuron, and therefore per microtubule if microtubules process information? So we have 10 to the 11 neurons. Therefore, that means that if all neurons are equal again, these are physicists' approximations, back of the envelope, simple estimates, then it means that we can have at most 10 to the 9th bits per neuron per second. Now that's the same number that we just saw, 10 to the 9th. Remember, 10 to the 9th was the amount of information that I estimated could be stored in the neuron through microtubules. So if we were to process that information, the maximum we could do is erase all of this information in 1 second. And that may be actually happening, right? If we receive input, some neurons may be receiving visual inputs and constantly updating these inputs. Maybe that's a realistic approximation of how much they can receive and store, and then change it on new inputs. Some sensor inputs are not always activated. At the moment, I don't seem to be smelling anything, so probably olfactory inputs are close to 0, but if they were, then very rapidly they can be encoded in the corresponding neurons. So now the question is, going deeper, so we know the limit per neuron, we know the limit per brain. Going deeper into the neuron, what would be, therefore, the amount of information you could process per microtubules, for example, or per microtubule? And that depends on the the time it takes to change a state. We call it the clocking time. The clocks for microtubules may be moving at a faster rate than clocks for neurons and clocks for the brain. Our clocks for human perception are typically 1 second, right? That's the grainness of our time. Anything that happens faster than 1 second, we probably don't notice. Maybe half a second, but let's say 1 second. And we probably remember things on the order of 1 minute, typically, or so. But inside the structure of our brain, things happen on a much faster scale that perhaps not all of it stays. Some of it is just constantly being erased, updated, and removed. So that depends how fast if microtubules change states on the order of 1 nanosecond, you can right away conclude that because the neuron can have 10 bits per second, or 1 bit per nanosecond, therefore all microtubules in the brain would have to be coherent. And if on that time scale of 1 nanosecond, all of them would have to be switching states in concert. If it's a slower time scale, then you can have inside the neuron microtubules doing different things separately. All right, so this is just a bit of a discussion for the audience to think about things that normally are not discussed, because these are, I would say, frontier areas of investigation in neuroscience. The question arises also whether microtubules are the only units that could be processing information. Probably not. Maybe ion channels. Ion channels operate on a millisecond time scale, and there could be hundreds of thousands or even millions of ion channels in a neuron. Therefore, each ion channel could encode independently, not coherently necessarily, because they are operating more slowly than microtubules. So perhaps a picture emerges where we have a hierarchical structure of spatial organization in the brain with, let's say, something on the order of 16 to 20 areas of the brain responsible for different processing tasks, visual areas or abstract thinking, etc. Within these areas, you may have groups of neurons subdivided into ensembles of closely interacting cells, and then inside each neuron you may have deeper layers of processing through ion channels and microtubules, maybe some other structures like actin filaments, etc. And each of these organizational manifolds has definitely a different spatial range, perhaps also time domain, going faster and faster as you go deeper and deeper, and a different energy requirement. So that could be called a fractal organization. It was actually proposed, or at least discussed, by Anirban Bandyopadhyay and his collaborators from Tsukuba, Japan, that published a paper which discusses this fractal organization of information processing in the human brain. Right. I assume that memory is simply encoding perhaps some kind of binary code on a molecular scale. But the definition of memory I haven't provided yet, so let's take a look at this. In general, I would say memory, whether it's human memory or artificial memory, is the ability to encode, store, and recall information. And there could be degradation of memory because of some wear and tear, because of damage. I would say, to my knowledge, there is nothing that I know that has perfect memory, whether it be magnetic tape or semiconducting devices or electronic devices, or even hieroglyphics or paper, whatever you use to store memories, yes, encode, and has over time degrades. Paper, stone, magnetic tape memory sticks. All these electronic devices have a finite lifetime. So in the current understanding of neuroscience, memory is represented by an interconnected network of synapses. So, but functionally, that is, activation of synapses is equated to the memory of some event or a structure, etc. And this is related to the strength, synaptic strength. So repeated activation causes so-called long-term potentiation. That is, if you repeat the same task or maybe memorize a poem, you activate the same synapses many, many times, and that causes easier activation of these synapses, which is called long-term potentiation. So the question of how is this achieved on a molecular level, is that the only thing? Can it be deeper? We'll come to it in a few minutes. And there were some interesting considerations in the past by various scientists. What is the capacity of human memory? And I mentioned this famous mathematical physicist, John von Neumann, earlier in connection with development of quantum mechanics. He also thought about this, being the godfather of computing, not quantum, but also quantum computing perhaps. He estimated that over our lifetime we accumulate about 3 × 10⁻20th bits of information in the brain. So remember, that's exactly the number I gave you based on the potential storage capability of a single microtubule extrapolated to the neuron and then to the brain. And that's exactly the same order of magnitude that John von Neumann predicted to be, which is actually vastly larger than other estimates. In the 1970s, some anatomists estimated this to be about 10 to the 13th to 15th bits. Thomas Landauer wrote a book, a paper in 1986 entitled How Much Do People Remember? And he assumed that we only retain about 2 bits of visual, verbal, tactile, and musical memory per second. Since we live about a few billion seconds, he then estimated that that we retain about 10 to the 9th bits, or in other words, 1 gigabit of information, which is, as you compare it to John von Neumann, 11 orders of magnitude too pessimistic, and according to the estimate that I showed you, that would be what 1 neuron is capable of remembering or storing. How do you put this in a historical perspective? So, agreeing with John von Neumann, I would say we are somewhere in this 10 to the 19th and 20th bytes of memory stored potentially. Perhaps some people remember more than others. It's interesting because under hypnosis, a lot of people remember details that otherwise we don't. So that must be a much greater storage than we could estimate just by interrogating somebody. Do you remember this? Do you remember that? What was the color of somebody's blouse or pants or ship? You remember that ship? The name of the license plate, or things of this nature, trivia. But perhaps deeper in our brain, these are stored pieces of information that can be recalled when you probe it much more diligently, shall we say. So, but to put it in perspective, and this is already perhaps outdated because we create so much information with digital media on a daily basis. That's a few years old, but at that time, perhaps a decade or so ago, the number of words ever written was by humanity was about 10 to the 16th bytes. Number of words ever spoken, 10 to the 19th. We speak less and I guess write more, so perhaps these numbers are now closer to each other. and the data on all digital media was about 3 times 10^19, which would be comparable to these estimates of human memory. In other words, we could potentially store everything that has ever been produced by digital media. That would be an astounding thing. But the question of where it's stored is still unanswered. We don't know exactly where. Some people propose some kind of holographic memory. One of them is Carl Pribram, a famous neuroscientist. He assumed that we produce some sort of hologram inside the brain, which is where memory. So it's not really physical in the sense of matter, but more electromagnetic. I mentioned the resonant model. Rupert Sheldrake, a popular science author, I guess reinvented the morphogenic fields of Gurwitch and claims that our memories are not stored in the brain at all, but we access them through the brain as if it was a receiver, and access it from some kind of a cloud, like computers today access the cloud, so to speak. So memories can be stored outside of us in space-time. Let's put it this way. No specific explanation exists. But there are some very intriguing experiments and observations that indicate, for example, memories can be inherited from generation to generation in terms of maybe skills and abilities. Even animals, mice, descendants of mice that solve mazes do it faster, as if they rewired the brains of their offspring due to the learning process. There's of course social memory that we talk about so much today, about traumatic memories of some groups of our society. Forget the term, but it is easy to imagine that things that previous generations experienced, some horrors of war, Holocaust, could be passed on to the next generation as some sort of burden, without really experiencing it, but feeling it on some level. It's interesting also, apparently plants can learn and adapt. Michael Levin at Tufts University is in my opinion, one of the most brilliant biologists, evolutionary and developmental biologists, and he has also studied this issue through experiments on slime molds, on experiments on worms and frogs, salamanders. Quite intriguing. I don't have the time to go into detail about his work, but I will mention only one example of his amazing insights into this topic. By the way, he believes that all of this has to do with bioelectricity, not genes necessarily, but bioelectric phenomena. One of the experiments he published in the Journal of Experimental Biology in 2013 is decapitating worms. First of all, training these worms to solve some maze problems, decapitating them and removing the heads, and letting them regrow the heads. And apparently, as reported in this paper, the worms were able to repeat their achievement. In other words, they retain the memory of the previous learning exercise following the decapitation. In other words, that would mean that memory is stored somewhere else in the brain, however small that brain may be. There's also a common belief that the brain is not the only thinking part of our body. We talk about the gut feeling, that is something that you can feel in the gut is maybe typically very intuitive, or some forewarning or something we experience at the gut level, as we say. Galvanic skin responses are used for lie detector applications, so our skin responds to stresses or tension or atmosphere feelings. So there is the electrical connection, as well as in the heart rate variability. So whether, and of course there's also the immune system, which is our second brain, the dynamically responding system of the body to pathogens and external threats. So there is probably more to memory than the brain, but microtubules are in all these systems, in all these cells. So perhaps there could be a somewhat adapted way of encoding through microtubules in different architectures and through different stimuli. Okay, that actually links to the topic of the living matrix, that the human body is interconnected matrix with signaling molecules, electric-enabled communication, and that also includes microtubules, perhaps other structures, other filaments, also extracellular filaments necessarily. Okay, there were some more specific experiments performed on memory, and it's easy to do this with animals, and in this case the experiments took place about 9 years ago, if I remember correctly. I think at Johns Hopkins, your former employer, where mice were trained, and again mice were trained to solve some mazes and acquire some skills in orientation, and then they were given a particular drug, pharmacological agent, which inhibits calmodulin kinase 2. It's an enzyme. I'll tell you about it in the next slide. And what happened is that that inhibitor actually allowed the mice to live more or less the same way as they did before, but they forgot everything. They were not able to solve these mazes. In other words, a claim that this is a memory inhibitor. And so, why is this linking us to microtubules again? Well, through the process of what we know, what calmodulin kinase 2 does in neurons, it's basically, in a nutshell, a read and write device at the molecular level. It is activated by calcium waves, and it forms a hollow enzyme. So, it's a very beautiful symmetrical structure. It's a motor protein which actually phosphorylates microtubules in the process. It has a phosphatase and kinase activity. Also involved in long-term potentiation through the calcium release. And in 2012, we wrote a paper which focused exactly on this enzyme. We tried to understand at the level of atomic resolution studies what it does, and because it was claimed that it phosphorylates microtubules, and so we tried to understand how it does so, and created, with Travis Crowther doing most of the work, created a computational model of this calmodulin kinase 2 enzyme, which is represented in various views in this slide. This is the top to bottom view, this is the side view of one layer, this is the enzyme shown sideways. It has a hexagonal structure, has 2 layers and a sandwiched group domain inside, and basically moves like a 6-legged creature on microtubules, some kind of a transformer, if you will, or nanorobot. And as it walks on microtubules, it phosphorylates or leaves a phosphate group on serine residues in C-termini. This is an electrostatic representation where blue is positive and red is negative charge, for a reason, as you will see. First of all, we have matched it to the microtubule surface. As you can see here, the matching, this is the calmodulin 2 kinase, this is the surface of a microtubule, 2 different lattices. It matches to both geometrically, it fits almost perfectly into a patch of microtubule. So geometrically is a perfect match between the calmodulin kinase 2 enzyme and the surface of microtubule. It also matches electrostatically. In other words, it's attracted to the surface of microtubule because of the charge complementarity, largely negative surface of a microtubule, largely positive surface of the calmodulin kinase motor domain, and it's just like other motor proteins. It's moved or propelled by ATP hydrolysis, which is sufficient to basically unbind it from the surface. So that's two views of the calmodulin kinase walking on microtubules. This is the length of a microtubule. It's crawling or walking on it like a six-legged, what would be how many legs do spiders have? Do you remember? Something's 8 maybe. Okay, let's say it's a six-legged spider, and here it is in the cross-sectional view. And as it does so, it leaves a trace of its walking. Of course, you can imagine many copies of this. So numerous such spiders working at the same time and encoding something. And what is it encoded in it? Well, it's phosphorylation, which means attaching a phosphate group to serine. On each C-terminus there is a serine, and that can be phosphorylated or dephosphorylated. And depending on whether it is phosphorylated, in which case you put a 1 bit, dephosphorylated 0, and so on. So you can suddenly see the creation of a code on the surface of microtubule with phosphorylation states. I mentioned this earlier when I counted the number of states. This would be the additional number of states you could add to the 10 to the 20th estimate. So, by the way, these could also be qubits, as phosphate could oscillate between two states, bound and unbound, in some kind of a superposition, if it's weakly bound. So, quite clearly you can see now developing what we call the brain code, maybe a secondary code, to long-term memory. Long-term memories could be some other states that I listed. This could be short-term memory, basically on stimuli coming into the brain, visual, tactile, etc., olfactory. The cost of each event is about 10 kT thermal units, so it's not easy to erase. There's still some probability of losing it by thermal agitation, but not very large. And so we called this brain's memory code. This is one possible hypothesis where and how this memory could be stored inside neurons and give us the potential that John von Neumann talked about, as well as link it to the experimental evidence of calmodulin kinase 2, performing the direct implementation of this writing and reading. What could be the implications or functional results of it? Well, by leaving these traces in particular states of and locations in microtubules, you could imagine this would affect motor traffic, kinesins and dyneins walking, and perhaps putting or avoiding phosphorylated states of C-termini, or vice versa. By the way, C-termini are the landing pads for kinesin motor domains. In other words, they bind there. And if you maybe you do the opposite, because phosphorylation would add negative charges, and kinesin motor domains are positive, so it could increase the binding affinity or increase the probability of landing there. If you dephosphorylate, the opposite, you reduce the probability. Also, microtubule-associated protein maps, MAP-tau, MAP2, there's a whole family of maps that regulate the internal connectedness of the lattices of microtubules and neurons. They also bind to C-termini. So that could also encode for binding or unbinding of maps, changing the architecture, and directing traffic from one microtubule to another. In other words, you could very quickly understand that this might be an evolvable computer in its own right, that is regulated by these kinds of external stimuli coming from the sensory receptors. And we've actually even proposed the formation of logic gates by these events. So the next step would be to create AND and exclusive OR gates involving microtubules and maps, depending on how they get phosphorylated by CAMK2, and that would be then realizable by the flow of either ions through these connections in the electrical form, or mass transport through kinesins. So I hope that this provides a little bit of a context for the importance of microtubules in the area of neuroscience. They form an interconnected matrix inside neurons, which so far has not been really properly, in my opinion, exploited. Even the Human Brain Project, the mega flagship that the European Union funded at the tune of 2 billion euros, stops at the level of 1 neuron, but doesn't go inside. And here we see an incredible, rich tapestry of possibilities in front of our eyes. So microtubules are responding to synaptic inputs and can be rearranged. We know that they are rearranged and as a result of stimuli and learning. Nancy Wolfe, my former collaborator from UCLA, devoted her career to understanding how cytoskeleton in neurons is affected by learning, for example, and reconstructed, influenced by information coming from the learning process, activates NMDA receptors and causes, again, the calcium influx, which triggers the breakdown of microtubules and maps. This then stimulates messenger RNA transport and local translocation of MAP2, CAMK2, NMDA-R, and then that, as a result, leads to the rebuilding of the cytoskeleton matrix to store synaptic information. So you can see the same players, as I mentioned earlier, in terms of memory, also participating in learning transformations due to learning at the level of intraneuronal architectures, the cytoskeleton, especially microtubule cytoskeleton. The flip side is destabilization of microtubules, and that's a huge area of pathology, neurodegenerative diseases, of which we hear more and more because of the aging population. Is typically a problem related to, is age-related. Quite often the trigger for many diseases, not necessarily the end stage, and also brain injury causes defects in microtubules inside neurons. But diseases such as Alzheimer's, Parkinson's, Huntington's, and Lou Gehrig's disease, some neurodevelopmental disorders, as well as brain cancer, lead to cytoskeleton disorganization. And without an exception, you will find microtubule and the cytoskeleton being affected by all of these diseases. Deterioration, whether it's the prime cause or downstream effect, we don't know for sure, but it's always there. In in either genetic cases, which are less common in Alzheimer's and Parkinson's. Typically it's sporadic, age-related and damage-related. DNA mutations or post-translational modifications cause misfolding of the protein, which leads to aggregation, which leads to loss of function, and finally neurodegeneration, death of neurons, and processing inability by brain domains. Loss of memory, as is the case with Alzheimer's, or tremors and movement disability, as is the case with Parkinson's. So it's an important issue for the healthcare system, for our population, especially the aging population, but not all aging. But as I said, in all of these diseases, although there are additional players, like in Parkinson's, there's alpha-synuclein and Parkin proteins, but there's always additional aspects of impaired exoplasmic transport, for example, or visible changes in the architecture of the microtubule cytoskeleton. Binding to microtubules changes. This is also seen in stroke and traumatic brain injury, pathologies, and you're an expert, maybe you've seen some slides. Pathologies of TBI show the disruption of microtubules in neurons. Concussions, there was actually quite a few years ago, there was a very large amount of information about concussions in athletes, professional athletes, football players, hockey players, having incredibly affected health status, longevity. I think in the US, in NFL players on average live 55 years or something of this order. And their brain pathologies indicated tremendous damage to intraneuronal structures. So the damage, the mechanical damage to the brain is actually transmitted to the breakage of microtubules inside neurons, which is quite amazing because we are protected by the skull and the fluid in which the brain is bathing. So at any rate, in all of this, including multiple sclerosis, where not only there is demyelination, but also disruption of axonal cytoskeleton. So let's just take a look at Alzheimer's disease as an example of this, which is very much in the spotlight, and we know the consequences are devastating to the patient and the family, loss of memory to the point of not recognizing the closest family members. But in Alzheimer's disease, there are two major molecular markers, one of which is hyperphosphorylation of tau, MAP tau, microtubule associated protein tau, which actually, so it gets overphosphorylated, hyperphosphorylated, and as a result, detaches from microtubules and forms tangles, ensembles of tau in a clump rather than interconnecting microtubules. In the context of what I just said about how we see memory and the brain code, this could be directly affecting the information flow throughout the neuron. The second aspect is beta amyloid, which accumulates in the extracellular matrix. It's outside neurons. Tau is inside neurons. Both are hallmarks of Alzheimer's disease. I think there's still a debate and two camps of neuroscientists arguing which is the primary, which is the secondary. We believe, or I believe, that actual microtubules are at the heart of it. Because of the fact that there's indication that beta amyloid formation is a secondary aspect because of the involvement of zinc. Zinc is necessary for the stability of microtubules. And it's depleted in Alzheimer's brains, which has been shown in various studies. So microtubules are weakened, and hyperphosphorylation of tau may be the next step, and then after that, zinc gets absorbed by the beta amyloid, which triggers accumulation, and feedback loop which self-propels, and therefore is a kind of never-ending process which deteriorates further and further. This shows you the schematic disruption of microtubule structure by hyperphosphorylation of tau, which is hyperphosphorylated here and accumulates there, and microtubules and microtubules are weakened and eventually disrupted and broken into pieces. These are some micrographs of tangles, tau tangles. This is a healthy area of the neuron. This is a diseased area with the formation of tangles inside tiny nerve cells. So there's a recent paper from 2018 showing that, contrary to what was believed before, tau doesn't stabilize microtubules, because the loss of tau maintains the size of the bulk of the microtubule, but depletion of tau causes the shrinkage of the labi part. Microtubules grow and shrink, and there is a so-called GTP cap, which is a few layers of around the plus end of a microtubule, which are being recycled or refreshed with new tubulin. So that's a narrow area of microtubules which is important for stability, but it's constant flux, and even in neurons. So that area without tau shrinks, but the rest of the microtubule doesn't. So the hypothesis, therefore, has to be revised or rethought, that perhaps there is something inherent with microtubules. Perhaps there are some misfolding of the protein tubulin, or some other post-translational modifications which affect the stability of microtubules themselves, not just tau. Okay. So the belief now is, or becoming to be accepted, that amyloid beta formation doesn't seem to cause spine loss, but microtubules destabilization causes spine loss, and loss of therefore communication between neighboring neurons. Okay, we have a few minutes left, and we've arrived almost at the end of this story, and at the most maybe profound question: what about consciousness? So we talked about correlates of consciousness, the things that happen in parallel to our cognitive processes. But what is really consciousness? And I think we really don't know. I want to come back to this aspect of quantum physics being involved in it, and perhaps microtubules will be the right place to look for these effects, and can support some form of quantum, definitely can provide storage for information processing, operational modes. But there is more to it, and this last thing I want to talk about is actually an insight into a direct knob that can turn consciousness off and on. We can't grab consciousness, but we can and measure it, but we can definitely quench it or remove it temporarily. And that, I think, is the best place to look for quantum consciousness. If there is such a thing. So that brings us to anesthesia, which is the best way of probing consciousness without actually doing harm. Although this is still an open question. Anesthesia probably causes some long-term effects, cognitive decline, but it doesn't kill the patient. It actually allows many patients to live, by allowing surgeries to take place. So what's interesting is that we still don't know the molecular mechanism of anesthesia, although we know many anesthetic molecules, I don't know, tens, perhaps on the order of 50 or more molecules which cause anesthesia in humans, animals. That's another interesting thing, that the same molecules which act on humans act on animals, roughly with the same potency. So that's good because we can experiment on animals if we want to find new anesthetics or test them. And what's interesting is that it has been determined in early studies that of all about 500 detectable proteins in neurons, tubulin is only one of 10 affected by halothane, one of the most common anesthetics, and only one of 5 altered or affected by isoflurane, which means that it's in a very small group of proteins that are for sure interacting with anesthetics. And the current hypothesis of how anesthetic gases act involves membrane receptors, but the problem is that there is no rhyme or reason for the chemical structures of anesthetic molecules. They can range from molecules with carbon and hydrogen chains to a single atom xenon or nitrogen molecule, or ring structures like propofol, ketamine, and so there is no common characteristic of anesthetic molecules. But all of these bind to tubulin, but there's not a single receptor that I could identify, or anybody for that matter, that shows, okay, here's the lock and key principle, all of these fit into the binding pocket. That doesn't exist for anesthetics. All these anesthetic molecules, as we say, are on pathway target. So microtubules are on pathway for anesthetic action. Therefore, if anesthetics get into the cell, they will interact with tubulin microtubules. What do? They bind weakly, but they have a multiple of binding sites on tubulin, as we've discussed and discovered through our computational work in some experiments. There is also interesting correlation with the action of anesthetics and the effects of chemotherapy drugs which act on microtubules, which would indicate that there is competitive binding. As we know, there is something called the chemo brain. Chemotherapy patients have some sort of they live in a fog, very impaired cognitive abilities, which means that there is probably effects of chemotherapeutic agents on the function, on neurons, and also patients which undergo simultaneously chemotherapy and get anesthetics, they are more sensitive to anesthesia than otherwise. So there is that, and there's more. So there are interactions between anesthetics and microtubules. We have discovered the binding sites on tubulin for all anesthetic molecules, and there are many of them. Some of them are actually overlapping with the known binding sites for drugs such as colchicine, zinc alkaloids, and we have found that actually they bind in all cases, or some of the cases anyway, very close to tryptophan residues. And tryptophan is an amino acid which is known to be excitable by electromagnetic radiation in the near visible range. And actually that links us all the way back to photosynthesis. Because tryptophans form these networks I talked to you about, which are very similar to photosynthetic light harvesting chain complexes, and so we have done calculations computer calculations on the excitations of these tryptophans and found the frequency at which they would coherently oscillate. I mentioned this earlier, but now we come back to what I talked about in the last lecture previously. And what happens is when you redo this calculation with the presence of anesthetics close to the tryptophans, the frequencies of these oscillations shift. And we have done this for about 16 different anesthetics and measured the shift of the frequency, downward shift, for all of them, and compared it to the potency of anesthetics. And there was actually, this is the illustration, in the paper published in 2015, I think another one in 2017, we showed the correlation between the amount of the shift of the inherent frequency of quantum oscillations in microtubule. So that's the, let's say, think about it as a natural frequency the microtubules support. Now you give anesthetic molecules to the system, and this frequency becomes lower. The lowering, the amount of lowering is in direct proportionality to the potency. Actually has a very high correlation coefficient, and until now, the only known molecular characteristic of anesthetics that made sense was the partition coefficient. In other words, the more lipophilic they were, the more potent they were. But okay, so they don't like water, they like lipids, they get into membranes, and then what? There's a lot of molecules which do that, and they have absolutely no anesthetic potency. So if you stay within the group of anesthetics, I would say, and that was the so-called Meyer-Overton relationship, which has actually a century-old history that was discovered in early 1900s, I believe. And we haven't made progress since, really. So I only want to make one more comment that in drug discovery, there's a concept of quantitative structure-activity relationship. In other words, you find quantitatively what structural features improve the activity of a drug or a proposed drug-like entity, okay? And typically, there are three major groups of properties that affect drug action. One of which has to do with the shape of the molecule, something to do with the shape. And that probably is related to lock and key. Whether it has a high affinity for the target. The second property has to do with something to do with solubility. And this is one of those. In other words, the environment. And the third one is always electronic. Something to do with the charge distribution on the molecule. Is there neutral? Is there a dipole moment? Is it negatively charged? Something like that. So, shape, solubility, electronics. In anesthetics, so far, only one such group has been, one such property has been looked at and correlates very well. And maybe that's the problem, that at that point they said, good, we have an explanation. But it's only one, and that's the lithophilicity. But here we introduced an electronic property, how anesthetics interact with the electronic degrees of freedom of the target protein, in this case tubulin. And the more they do, the better, the more potent they are. So what I'm trying to say is that these two things are not in contradiction to each other. They may be actually cooperating, explaining two aspects of the anesthetic molecules. The first one, they have to get into the cell, and to get into the cell, they have to have an ability to bind to the membrane and go through the membrane. And the second is, once they are in, they have to interact with the target, in this case microtubules. So that will be, once again, quantum representation, because we talked about the quantum Hamiltonian that explains these oscillations, electronic degrees of freedom. A clear example of quantum biology serving medicine in terms of anesthesia. I'll stop at this point and And I thank everybody for your attention.